Alrighty, I hope you guys are doing well on this Friday afternoon. Does anybody have any questions about any homework or ICA problems before we start learning about mesh analysis?
Could we do homework 5, problem 3?
Homework 5, problem 3. All right, West, which part in particular?
Part B.
Part B. Okay. So that's one of the ones where I told you guys specifically to wait until you learned how to do nodal analysis and all that kind of stuff. So let's tackle it using nodal analysis. So if it's okay with you guys, I'm just going to solve this symbolically, meaning that I'm just going to set up the equations and all of that kind of stuff. And then you guys should be able to just, put in your numbers and come out okay. So let's see. So the circuit looks something akin to this, where we've got some current source here, I1, connected in parallel with some resistor R1. Then we've got this dependent voltage source, 5IY. Here is some resistor R2, and the current flowing down through R2 is our controlling variable IY. And then lastly, over here on the right, we have a current source I2. So West, since you're asking about this problem, I will let you choose where to put our reference node. Do you have any opinions?
Um, the top right one.
Top right. Okay, so let me identify those nodes real quick just by coloring them in. And if we put our ground at the top right node, so I'm just going to do it like this. So I'm going to call this guy right here node A, and this guy down here node B. Um, so we have a controlling variable, IY. So we're going to have a controlling variable equation. And in this case, since the current is starting at ground, we're going to do 0 minus. It's flowing towards node B, so that's 0 minus VB, or just negative VB divided by R2. We have a voltage source, so I'm going to put a circle around it like so, uh, indicating our supernode. We're going to have a voltage relationship equation. So that's this guy right here. And let's see, so the nodal voltage at the positive polarity terminal of that source is ground. So I'm going to have 0 minus. The nodal voltage at the negative polarity terminal is VA. So we have 5IY is equal to negative VA. And the last thing that we'll need to do is just write a KCL equation at node B. So that's going to be these four currents in the direction that I've indicated. So that would be I1 plus VB minus VA over R1 plus VB over R2 plus I2 is equal to 0. And so solving this system, where our variables are VA, VB, and IY should allow us to get the answer for IY that we're looking for. Um, any other questions about either this problem or any other problems? All right, well then let's mix it up with mesh analysis. So mesh analysis is very similar to nodal analysis in as much as we're going to wind up setting up a system of equations. While nodal analysis used Ohm's law and Kirchhoff's current law, mesh analysis is going to wind up using Ohm's law and Kirchhoff's voltage law. Okay, so we're going to start our understanding of mesh analysis by looking at circuits that only contain voltage sources, and then we're going to see how current sources tend to mess some of our relationships up and how we'll deal with that. Much like we did in class on Wednesday, we're going to kind of learn by doing. So I'm just going to make up an example problem, and then we will go from there. So let's say that this is our circuit of interest. I've got a 10 ohm resistor here, a 7-volt source here, a 5 ohm resistor here, an 8 ohm resistor here. Let's put a current controlled voltage source here. So let's say that this is 3ix, and let me just put another resistor over here to the right. So this will be 15 ohms. And I'm going to define my current Ix as the current flowing down through this 5 ohm resistor. Okay. So our first step when employing mesh analysis is going to be to identify our mesh currents or identify our meshes. And then our second step is going to be to assign our mesh current. So I'm going to kind of roll this all into one step. So do any of you guys remember what our definition for a mesh is? This is something that we actually talked about on the very first day of class towards the end.
Isn't it a loop inside a bigger loop?
So a mesh is any loop which doesn't contain any smaller loops. So I guess realistically, what you said is correct, but we might not always have a mesh, I guess, inside something larger. So for this particular circuit, there would be 3 meshes, one on the left-hand side, one in the middle, and one on the right. And I'm going to go ahead and assign those mesh currents as follows. So I'm going to assign some mesh current, let's call it IA, that's circulating around this left-hand mesh. Let's have a mesh current IB that's circulating around this middle mesh. And lastly, let's have a mesh current IC that's circulating around this right-hand mesh. Now, I always write my mesh currents flowing in a clockwise direction. That being said, you could choose to write your mesh currents in a counterclockwise direction, or you could choose to use some combination of the two. I personally find using a combination of directions a bit confusing, but to each their own. I know a lot of mechanical students, I think like to write their meshes in a counterclockwise direction because I think that's the direction of the arrow that you would use to define your moment of inertia or something like that. It's been a long time since I had static, so I may be misremembering, but I'm always going to do clockwise. Okay. So what these mesh currents represent really is just the current that's flowing around the perimeter of the mesh. So this mesh current IA that I wrote here in red is really just the same thing as the current that's flowing up through the 10 ohm resistor. The mesh current IB is really just the current that's flowing to the right through the 8 ohm resistor, and the mesh current IC is nothing more than the current that's flowing down through the 15 ohm resistor over here on the right. So we can tie this concept of a mesh current back to other things that we've done before. This is really just kind of using once again, a shorthand notation so that we can kind of sort stuff out. Okay. So before I erase these extra things, does anybody have any questions about identifying our meshes, assigning our mesh currents, or anything like that? All right. So our next step is going to be express our controlling variables in terms of our mesh currents. So our controlling variable in this circuit is that current Ix. So Ix is defined as the current that's flowing down through the 5 ohm resistor. And that 5 ohm resistor is shared between the left mesh A and that middle mesh B. So because that resistor is shared between those two meshes, what we're going to find is that we're going to have to express that current in terms of both mesh current A and mesh current B. Okay. So what we're looking for is the current that's flowing, the mesh current that's flowing in the same direction as Ix as it passes through that 5 ohm resistor will get a positive sign, and the mesh current that's flowing in the opposite direction of Ix as it passes through that 5 ohm resistor will get a minus sign. So here, as IA flows around its clockwise path, when it hits the 5 ohm resistor, it is flowing down, which is in the same direction as Ix. So we'll have positive IA, and IB, as it flows around its clockwise direction, is going to wind up flowing up through the 5 ohm resistor, which is opposite the direction of Ix. So we'll have minus IB. If instead we had a controlling variable that was a voltage, we would do the exact same thing, except that we would just multiply that total current flowing through the element times the resistor value itself, which is what we're going to wind up doing here in a moment when we start writing our KVL equations. So does anybody have any questions about how I chose the signs for my IX relationship? All right. So step number 4 here is just going to be to write a KVL equation around each mesh. So we would start with mesh A, so I'll have KVL at mesh A, and I'm going to write these KVL equations exactly like I did on the, I guess it was the 3rd day of class. I'm going to start from the bottom left-hand corner, and I'm just going to follow that mesh current around until I wind up at the same node that I started from. So we are always going to assume that the mesh current that we're following is flowing into the positive polarity terminals of any resistors that we see, okay? So that means that I would have 10 ohms times IA is my first term in my KVL equation for mesh A. Then I see the positive polarity terminal of the 7-volt source, so I'll have plus 7 volts. And now I see the 5 ohm resistor. And as we discussed earlier, there is a total current of IA minus IB flowing down through that 5 ohm resistor. So I'll put IA minus IB here. And now I'm back at the node where I started from, so I'll just set this equal to 0. So before we move on to our KVL equation for mesh B, does anybody have any questions about where any of those terms came from? All right. So when we write our KVL equation for mesh B, we're now following mesh current IB around. So anything that's flowing in the opposite direction of IB is going to wind up getting a negative sign. So the first thing we see is our 5 ohm resistor. And now that we're following IB around, we'll have 5 ohms times IB minus IA. Again, we're always assuming the current we're following is flowing into the positive polarity terminal for any resistor voltage drops we're dealing with. The next thing that I have is going to be the 8 ohm resistor, and it has a current of just IB flowing through it because that particular resistor is on the edge of the circuit. Then we have our dependent voltage source, which is going to look like 3Ix, and we are back to the node we started from, so this is equal to 0. Any questions about our equation for mesh current B? Okay, lastly, we have KVL around mesh C. So the first thing that we see is the negative polarity terminal of that dependent source. So that'll be minus 3Ix. Then we have our 15 ohm resistor, and the only current flowing through that guy is IC. So we set it equal to 0, and we now have 4 equations for our 4 unknown quantities. Realistically, I would probably substitute this Ix relation into equations 3 and 4 here, so that I could solve this as a 3x3 system with my calculator. So I'm going to do that just real quick like. So let's see, this is going to be 5 ohms times IB minus IA plus 8 ohms IB plus 3 IA minus IB. For this guy over here, that's going to be negative 3 IA minus IB plus 15 ohms IC is equal to 0. And I'm just going to pretty this equation 2 up as well by moving my constant term over. So that's going to look like 10 ohms times IA plus 5 ohms times IA minus IB is equal to negative 7 volts. And now I'm going to solve these 3 equations in my calculator real quick. So using my 3x3 system solver, in my first equation, my coefficient for IA is 10 plus 5. My coefficient for IB is negative 5. My coefficient for IC is 0. And my constant term is negative 7. In my second equation, my coefficient for IA is minus 5 plus 3. My coefficient for IB is 5 plus 8 minus 3. My constant term is 0. Oh, sorry, my coefficient for IC is 0, and my constant term is 0. And then in my last equation, my coefficient for IA is -3. My coefficient for IB is +3. And my coefficient for IC is 15. Constant term is 0. And so when I solve this system, so that would actually be step number 5. I would find that IA is equal to -0.5 amp. IB is equal to -1/10 of an amp. And lastly, IC is equal to -2/25 of an amp. So if anybody was following along with your calculator, could you let me know whether or not you got the same results?
Yes, sir.
Good deal. So this is the basics of mesh analysis. Like I said, it's very similar to what we did with nodal analysis, except that we're just using KVL instead of KCL. So before we move on to, breaking things with current sources, does anybody have any questions, comments, or concerns? All right, so let's mess things up with current sources. I'm not going to give you guys something crazy that we have to solve using MathCAD today, just because the process for using MathCAD for mesh analysis is so similar to nodal analysis that I don't feel like we need to really, beat that horse anymore. So I'm actually going to look at homework 5, problem 3C, and we're going to approach this guy using mesh analysis. So here is the circuit that we are interested in. I am going to throw some numbers at this for us. So let's see. Let's say that this is 51 ohms. This will be 28 volts. I apologize if you guys can hear my dog barking. I've got a gentleman here working on my HVAC unit, and my dog has decided that she needs to let him know that she is here also. This is a voltage controlled current source. 18 ohm resistor across which we have our controlling variable Vx. Let's see, this guy is going to be 16 volts, and I'm going to add a little something to this. So I'm going to give myself another mesh over here to the right because I want to illustrate something else to you guys. So let's make this 25 ohms, and let's give us a 2 amp source over here. Okay. All right. So a lot of our setup is going to be exactly the same thing that we did a moment ago, right? So lumping together our first two steps, we are once again going to simply identify our meshes. and assign our mesh currents. So once again, this guy on the left will be IA. This guy in the middle can be IB. And this guy over here on the right can be IC. Step number 3 is once again going to be to express our controlling variables in terms of our mesh currents. And in this case, our controlling variable is the voltage Vx. So would anyone like to volunteer and tell me how you would express Vx in terms of our mesh currents?
Would it be IB minus IA?
So it's a voltage, so it's not just going to be a current by itself or a combination of currents. We're going to wind up using Ohm's law, right? So Vx is the voltage drop across the 18 ohm resistor. So we would do 18 ohms times the current flowing through the 18 ohm resistor. So what's the current flowing through the 18 ohm resistor? Or what's the mesh current flowing through the 18 ohm resistor?
IB.
IB, exactly right. So whenever we have a resistor that's on the edge of the circuit, like the 18 ohm resistor, we're only going to have one mesh current flowing through it. So that's why it's just IB in this case. Thank you for that. So instead of skipping the extra steps, like we did with nodal analysis the other day, I'm just going to kind of get right to business here. And I'll explain essentially what the problem is when we get to that point and why we have to make these changes. So much like we saw in nodal analysis, whenever we had voltage sources, in mesh analysis, whenever we have current sources, we are going to have current relationship equations, okay? So our fourth step is going to be to write a current relationship equation for each current source. Okay. So I'm going to start with the 2Vx source here. And so our current relationship equation is going to be pretty simple. Whichever mesh current is flowing in the same direction as the current source gets a plus sign, and whichever mesh current is flowing in the opposite direction of the current source gets a minus sign. So since this 2Vx source is shared between meshes A and B, we're going to have either IA minus IB or IB minus IA. So I'd like for one of you guys to tell me which one of those two options it is.
IB minus IA.
Exactly right. Thank you. Now over here to the right, we'll tackle our 2 amp source. Okay. So because this 2 amp source is only touching mesh C, we're only going to have the IC term. So now the question is, if IC is flowing in the same direction as our current source, it gets a plus sign. And if IC is flowing in the opposite direction of our current source, it gets a minus sign. So should this be 2 amps is equal to positive IC or negative IC?
Negative.
Negative IC, thank you for that. So those are our current relationship equations. Nothing particularly wild or crazy there. Okay. So our fifth step is going to be to write a KVL equation for all supernodes. And I'm going to put here in parentheses, if possible. Okay. So, excuse me, that should say super mesh. So I have yet to define what a super mesh is. So I'm going to do that now. Okay. And I'm going to explain it in context of if we were trying to write a KVL equation around mesh A. Okay. So if we were trying to write a KVL equation around mesh A, we would be going up through the 51 ohm resistor. Okay. That's how we would start. So that would just be 51 ohms times IA. Nothing problematic there. Now, as we follow IA around its clockwise path, we would be going for the voltage drop across the 28 volt source, which is just going to look like plus 28 volts. Again, nothing problematic there. But when we try to write the voltage drop across our current source, we run into a problem. It is literally impossible for us to write or express the voltage drop across that current source in terms of our mesh currents. So what we're going to do instead is we're going to bypass it, okay? And we're just going to keep on going. So I'm going to do this in purple. So we've got this guy here, and now I'm just going to go across over here and wind up closing the loop down here. So this is the path for our super mesh. And this super mesh is really just the smallest combination of meshes possible that avoids us taking the voltage drop across that current source. So if our current source is between meshes A and B, we'll just smash meshes A and B together and write a KVL equation around both of them. Okay, so our KVL relationship here, so KVL at super mesh AB would simply be 51 ohms times IA plus 28 volts plus 18 ohms times IB plus 16 volts is equal to 0. So does anybody have any questions about where those particular terms came from or anything like that for that KVL at supermesh AB equation, or any questions about the concept of a supermesh in general? All right, our last, or I guess our next to last step would be to write a KVL equation for all remaining meshes. And once again, I'm going to put this caveat here, if possible. So the only remaining mesh that we could,
Trevor asked a question.
yeah, I saw, what if the dependent source is on the outside? So what do you mean by on the outside? Do you mean on the perimeter of the circuit, Trevor? So we're going to hit something similar to that here if we try to write an equation around mesh C. So it doesn't really matter whether or not we have a dependent current source or an independent current source. We're going to have problems anytime we have a current source. So if we try to write a KVL equation around mesh C, we first, go up through the 16-volt source. So we would have minus 16 volts, then plus 25 ohms times IC, and then we hit this current source and we literally can't do anything, okay? So whenever we have a current source on the edge or the perimeter of the circuit, we don't write a KCL equation. So I want us to look back here and think about something real quick. How many total unknown quantities do we have?
4.
4. So we have our three mesh currents, IA, IB, and IC, and our controlling variable, Vx, okay? How many equations have we written?
4.
4. So we don't actually need any more. So that's why I have this caveat here, if possible, because we're going to run into cases where we literally can't write a KVL equation. So the order that I have you guys write these equations in is to eliminate that kind of ambiguity, right? So we already have our 4 equations, so we can skip step 6 because there's literally no relationships left for us to come up with, okay? So our last step here would then be to simply solve this system of equations. So let's see which one. What I'm going to do is I'm going to wind up substituting this equation right here into this guy down here. So I didn't give myself a heck of a lot of room, so hopefully this doesn't make this too confusing. So 2Vx is going to look like 36 ohms times IB. So we could have 36 ohms, or actually let me just do it as twice 18 ohms so that we know where that's coming from. I'm going to pull that IB from the right-hand side over. So I'm just going to have minus IB plus IA is equal to 0. So here's 1, 2, and 3 equations. Another substitution that we could have made would just say that IC is equal to negative 2 amps, and then we could have solved our 3 equation, 3 unknown system for unknowns IA, IB, and Vx. Whatever substitution you want to make works, okay? So I'm going to solve this system really quickly. So in my first equation, my coefficient for IA is positive 1, and my coefficient for IB is going to be 2 times 18 minus 1. My coefficient for IC is going to be 0, and my constant term is 0. In my second equation, my coefficient for IA is 0, my coefficient for IB is 0, my coefficient for IC is negative 1, and my constant term is 2. And in my third equation, my coefficient for IA is 51. My coefficient for IB is 18. My coefficient for IC is 0. And let's see, my constant term is going to be negative 28 minus 16. And so when I solve that system, I found that IA was equal to negative 0.87153 amps. IB is positive 0.02490 amps. And IC is negative 2 amps. So if anybody was following along with their calculator, did you get a similar result?
Yes, sir.
Good deal. Okay. So this is really the bulk of mesh analysis. There are a couple of special cases that you might see every now and then. And I actually have one of those special cases in class assignment problem number 3. So I'm actually going to work that guy with you all here. A, because it's representative of the stuff that I kind of like to do on the tests, and B, because I want to make sure that you're not confused about things, okay? So before I open up that ICA assignment, does anybody have any questions? All right. So let's look at problem 3 here, okay? So we've got our circuit here. We're asked to use mesh analysis to determine the voltage Vx and then also the power supplied by each of the sources in this circuit. So we're going to use this as an example of not only mesh analysis, but also, what you can do with mesh analysis in terms of finding unknown voltages and things like that as well. Okay. So I hope it's obvious to you guys, but we have 3 meshes that we're going to deal with here. So this is going to be mesh current A. I'm going to call this guy over here to the top right mesh current B. And down here in the middle, we're going to have mesh current C. Okay. So I have identified and labeled my 3 meshes, and I have assigned my mesh currents. So our next step should be expressing our controlling variable in terms of our mesh currents. And actually, I'm going to rewrite this mesh current A because I don't want it to get in the way. So I'm just going to put it over here like this. Okay. So before I show you guys something, does anybody have any thoughts on how we might express our controlling variable Vx in terms of our mesh currents? Because there are a couple of different ways that we could do this.
Is there a way you can make it into super mesh?
So mesh A, or I guess a better way to put this, Vx isn't touching any current sources, so that's not really going to work for us. Okay. So I like to put these diagonal voltages here and stuff like that to make you guys think. So we're going to investigate 2 different ways that we could do this. Okay. So the first way that I could do this is I could write a KVL equation around this kind of triangular path right here. Okay. So we would have, starting from the bottom point of the triangle, we would have plus Vx. And now we have the 5 ohm resistor. So what mesh current is flowing through the 5 ohm resistor in the direction that's indicated as we follow that path around the triangle?
IA.
IA, exactly right. And the next thing that we would have would be the 16 ohm resistor. What's the current flowing down through the 16 ohm resistor?
IA minus IB.
Exactly right. And we would set this equal to 0. So rearranging here, we could say that Vx is equal to negative 5 ohms times IA plus 16 ohms times IB minus IA. Or I could just as easily have made that a negative sign as well and left it as IA minus IB. Either way works, okay? So that's one way that we could solve for Vx. And there's technically nothing wrong with that, but there's an easier way to do it, okay? So let's think about this really quickly. Let me use this color. So this negative polarity terminal is associated with this node over on the left-hand side of the circuit. So we've got a positive polarity terminal here at this node, and the negative polarity terminal could be written as here on the left of the 21 ohm resistor. So another way to think about that voltage Vx is it's literally just the voltage drop across the 21 ohm resistor. So that would be Vx is equal to 21 ohms times, so IA is the mesh current that's flowing into the positive polarity terminal, and IC is the mesh current that's flowing into the negative polarity terminal. And for what it's worth, if we had done KVL around this triangular path, we would have gotten the exact same result, okay? So realistically here, you can just use whichever method makes the most sense to you. So you can always rely on using Kirchhoff's voltage law for defining any voltage, or if you think your way through it, in this particular case, we could have also just used Ohm's law. So just to be clear, this was intentionally tricky. And you will likely see things like this on both your homework assignments as well as your exam. Okay. So before we move on to the subsequent steps of mesh analysis, does anybody have any questions about how I defined Vx here? All right. So somebody refresh my memory. What should our next step be?
I should write the KVL equations.
I don't believe so, because we've
Oh,
got
I'm sorry.
current sources.
It's the equations for your dependent variables.
So we just did that one. That's where we define Vx. So we're missing the one in between, which should be our current relationship equations. Let me double check. So we did step 1 and 2. We did step 3. Now we're at step 4. Write current relationship equations for each current source. Okay. So I'd like you guys' help with these. Let's start with the 0.5 Vx source. So which mesh current is flowing in the same direction as that guy?
I see.
And which mesh current is flowing in the opposite direction?
IB.
Thank you for that. Now we have our 7 amp source. So it's on the perimeter. So is it going to be plus IC or minus IC?
Plus.
Plus IC. All right. So there are our current relationship equations. Before we move on from here, does anybody have any questions about those guys? Okay. And so now we get to the step where we would write a Kirchhoff's voltage law equation around our supernode. Okay. Excuse me, super mesh. So this is one of those anomaly kind of things. Okay. So I want to explain what I mean by that. Okay. So we have a current source that is shared between meshes B and C. Okay. So this guy in the middle is shared. So in our previous example, we simply combined meshes B and C together. So going around mesh B, like so, we can't go through that path that contains the current source, so we would keep on going down here, and well, damn, I hit another current source. So it turns out that whenever we have a super mesh that contains a current source on the perimeter, we can't write a KCL equation for that guy either, for the exact same reasons as before. So that's why I put that, if possible, right here as well, because there will be rare cases where it is literally impossible for us to write a KVL equation around our supernodes. Excuse me, super meshes. Sorry, I keep mixing those up today. So since we can't write a KVL equation around our super mesh because our super mesh contains a perimeter current source, the next thing that we could do is just jump down to step number 6. Write KVL equations for all remaining meshes. So what's the remaining mesh that we have here?
IA.
Exactly right. So we'll just write a KVL equation around mesh A, and that'll be it, because we've got, so I'm going to put one equation for both of those guys because we wouldn't use both of them. It would just be one or the other. Here's our second equation. Here's our third equation. So the only thing that we have left is just KVL around mesh A. So to me, actually, I want you guys to tell me this. I don't think I've had you explicitly just tell me what's going on for a KVL equation yet today. So starting from the bottom left-hand corner and going around mesh A, what would we see?
5 IA.
So 5IA, thank you for that. What comes next?
Shouldn't it be 16 times IA minus IB?
Exactly right, thank you. And what's our last term going to be?
21 ohms times IA minus IC.
Exactly right, Joseph, thank you. There's our fourth equation. And so what I'm going to do this time is just anywhere that I see IC, I'm going to replace it with 7 amps. So that way we don't need this guy right here. Okay. So my variables, when I put them into my calculator, are going to be IA, IB, and VX. Okay. So starting with the equation that I have labeled 1, my coefficient for IA would be 21. My coefficient for IB is going to be 0. My coefficient for Vx is going to be -1 when I move it to the other side of the equal sign. And then my constant term is going to be 21 times 7 when I move it to the other side of the equal sign. For my second equation, let's see, I'm going to leave the 7 amps on the right-hand side of the equal sign and move the IB over. So my coefficient for IA is 0. My coefficient for IB is +1. My coefficient for Vx is 0.5. And my constant term is 7. And in my last equation, which I have labeled as 4 here, my coefficient for IA is going to be 5 plus 16 plus 21. My coefficient for IB is going to be -16. And my coefficient for Vx is 0. And my constant term is going to be positive 21 times 7. And assuming I haven't made some jackass mistake here, which is always possible, knowing me, I got IA as 41/6 amps, IB as 35/4 amps, and VX as negative 3.5 volts. Okay, so I'm hopeful that I haven't made any egregious mistakes here because I did get the right answer for VX. Before we talk about solving for powers, did anybody else get similar results when you put this into your calculator?
I just didn't know what equations to plug in all honesty.
Sure. So let me reorganize these guys so they're maybe a little bit easier to follow what I was doing here. So let's start with this guy right here, right? So I had 21 times 7 amps is equal to 21 ohms IA minus VX. So if the algebra doesn't make sense, please let me know because there's a huge possibility that I've made a dumb mistake here. But what I'm trying to do is move VX over from the left-hand side to the right-hand side, and I'm trying to move my constant terms from the right-hand side of the equal sign to the left-hand side. So I believe I algebraed that correctly, but I'm bad at it sometimes, so perhaps I've made a mistake.
I got it now.
Okay. For this guy right here, I'm just going to move IB over. So I would have IB plus half of VX is equal to 7 amps. And then for this guy right here, really the only thing that moves over is that 21 times 7 amps. So 5 ohms IA plus 16 ohms IA minus IB plus 21 ohms IA is equal to 21 ohms times 7 amps. All right, so I'm going to be more arrogant than usual and just assume that my answers are correct. And now let's talk about power. Okay. So we're asked to determine the power supplied by each of these sources. Okay. So I'm going to define a voltage drop across my 7 amp source. Let me see what color to do it in. Let's do it in this hot pink thing. Okay. So because I'm trying to find power supplied, I want to put my negative polarity terminal over here so that the current is flowing into the negative polarity terminal and out the positive polarity terminal. And I'm going to call this voltage here V7 amps. So does anybody have any thoughts on how I might solve for that voltage V7 amps? Because I obviously need that in order to determine the power supplied by that 7 amp source.
Could it be in parallel with something?
It isn't. Or, I mean, I guess technically it's in parallel with a combination of several things, but yeah.
Did you multiply it by the REQ?
So I don't know that we've really discussed what equivalent resistances look like when we have dependent sources. we're actually going to handle that next Friday. So I won't make you guys guess anymore. We're going to write a KVL equation. And our goal here is to just choose a path where that voltage V7A is our only unknown quantity. So what about the perimeter of the circuit? Right? That's our only unknown quantity if we've already found all of our mesh currents, right? So we could say that our voltage V7A, I'll do it down here, is going to wind up being equal to 5 ohms times IA plus 20 ohms times IB. Which to me comes out to be 1,255 over 6 volts. And so the power absorbed by our 7 amp source is just 1255 over 6 times 7 amps. Comes out to be 1464.167 watts, or 1.46, excuse me, 4 kilowatts. So what I'm trying to impart to you guys right here, and I feel like I'm doing a shitty job of it, so I apologize, is that once we know what our mesh currents are, we can use KVL around literally any path we choose to find any unknown voltage that we might be interested in, even the voltage drops across current sources. And it's because once we know what all of our mesh currents are, the voltage drop across this 5 ohm resistor, we can find it just using Ohm's law. The voltage drop across this 20 ohm resistor, again, we can just find that using Ohm's law. So they are essentially known voltages to us. Okay. So now let's talk about how we would approach the dependent source. Okay. So I'm going to assign a voltage drop across the dependent source. Let's call it VDEP right here. I want the current flowing into the negative polarity terminal and out the positive polarity terminal like so that we'll just have supplied power. And so now we could write a KVL equation around mesh B. To find that VDEP, we could write a KVL equation around mesh C, since we know what V7A is. Or we could write a KVL equation around meshes A and B. Really, any mesh where we wind up going through that path across the voltage source, excuse me, across that current source is now fair game. I'm going to choose to do it by writing a KVL equation around mesh B, right? So we would have 16 ohms times IB minus IA plus 20 ohms times IB plus 25 ohms times IB minus IC plus VDEP is equal to 0, which means that the voltage drop across our dependent source is just going to be 16 ohms times IA minus IB minus 20 ohms times IB plus 25 ohms times IC minus IB. And I'm just going to throw that into my calculator real quick. And remind myself that we found that guy to just be 7 amps. So 16 times x minus y minus 20y plus 25 times 7 minus y comes out to be negative 2,993 over 12 volts. And from here, we would have negative 2993 over 12. And then our current is half of Vx. So 0.5 amps per volt times the Vx that we found of negative 3.5 volts. And I just got 436.479 watts, which is indeed the answer. Alrighty. I know that particular problem was a lot. That's why I wanted to kind of work it with you guys. Does anybody have any questions? Okay. Well, I don't have anything else that I particularly want to talk about today. So feel free to use the remainder of our class time to work on problems 1 and or 2 from the in-class assignment. For what it's worth, I believe them to be much easier than this one. And if you choose to enjoy the rest of your Friday afternoon, I hope you guys have a safe and happy weekend, and I'll see you on Monday.